The network is the computer, revisited. Quick disclaimer, the opinions expressed are my own and not necessarily those of you or anybody else. But they are open source, so feel free to share them around. Hello, my name is Chris Hertel. A little bit about me. I'm a storage developer. I'm a weekend cyclist. I've been with the Samba software team for many, many years. I started up a project called JSIFs a while back, and I wrote a book on SMB3 internals. I also led the contracting team that wrote the official SMB1 specifications for Microsoft. I've done a lot of highly visible work on SMB1, but that's really just the bright, shiny tip of the iceberg. My career has, so far, been somewhat eclectic, and I have enjoyed almost a lot of it. A quick aside, I remember going to the beach as a child. I remember being so excited when we arrived. I would run down the beach, chasing the water as it receded, and then I would be surprised when the next wave rolled in and crashed down on top of me, knocking me over and leaving me soaked and sputtering and sitting in the sand as the wave that had just slapped me down receded to make way for the next. That, to me, also describes how innovation rolls ashore in our industry. It comes in waves. Waves that sometimes surprise us, catch us off guard, even though we saw them rolling in when they were a long way off. The current wave of new, smarter, more versatile network infrastructure is technology that was expected, but I was still knocked onto my sandy bottom when it crashed down over me. I'm here to provide you with the whys and wherefores of a little project I'm working on called Zambezi. We'll be talking about the newest wave of SmartNICs. There will be a quick discussion of software-defined network switches and their possible use in creating software-defined network-attached storage. We'll throw in distributed file systems just for fun, and then return to Zambezi to see how it all fits together. So, the Zambezi project. Why is it called Zambezi? Well, it needed a name. Perhaps I was thinking SMB Easy or something. It isn't really important. The project just needed a name. So here's a quick overview. Zambezi is a toolkit. It was originally aimed at embedded devices and application development, sort of like JSIFs. When I started writing code, I started with low-level functionality, marshalling and unmarshalling packets. I'm currently working on transform headers for encryption and compression. All of this code works at the message syntax level. Since it's a toolkit, one of the things I realized was that the API would need to be well-defined. I'm keenly aware of the separation between the syntactic and semantic layers of SMB. Even the official SMB documentation separates out these two aspects. The semantic layer deals with things like file system behaviors, locking and leasing, ownership and access controls, integration with the underlying OS and the file system. For now, writing code for the SMB semantic layer is out of scope for the Zambezi project, and that's a good thing. So, what can we do in the lower layer of the SMB stack? We've already talked about message handling. We'll also need to handle message syntax errors and transport errors. Connection negotiation and feature management could also be handled at this layer, possibly more, depending on what is passed down to us from the upper layer. We will, of course, still need a well-defined API. Working on this, I began to realize that this could all be neatly packaged and pushed off to a SmartNIC. SmartNICs are already used for TCP and iSCSI offload. Why not SMB? SmartNICs and end-to-end arguments. Our industry is full of folks who know a lot about this or that specific technology. If you are already familiar with the current crop of data processing units and are familiar with software-defined networks built on network operating systems, then you have probably already gotten to the main point of this presentation. I'm going to share my own emerging understanding of these technologies in relation to SMB. We'll start, though, with end-to-end arguments. I'm a bit of a tangential thinker. Give me 2 points on a Euclidean plane and watch me draw circles getting from one to the other. 40 years ago, a paper came out from MIT called End-to-End Arguments in System Design. It gathered the collected wisdom of network design from past years, made sense of it all, and set the standard for years to come. These are standards we still live by today. This paper was recommended to me by a computer science professor at the University of Minnesota. I just happened to be taking a graduate computer science class at the time, and it was kind of an assignment, but it made a big impression on me. The first sentence of the main text says this: choosing the proper boundaries between functions is perhaps the primary activity of the computer system designer. When working with network offload, it is necessary to identify the logical endpoints of any given form of connectivity. What are the logical endpoints for compression, for encryption, for the underlying transport, for connection negotiation and maintenance? This little diagram that I've thrown together at the bottom of the screen shows on the left a corporate network that has, among other things, a storage array and a WAN accelerator. On the right, there is the other end of the accelerated WAN, and an end user trying to access files and services. WAN acceleration works best if the data that is passing has not been encrypted or compressed already. Let the WAN accelerator do its job. But in SMB3, the client and server can negotiate encryption or compression. Perhaps encryption is required within the local networks. So we have a border dispute. If the WAN accelerators are SMB3 enabled, however, then we can proxy the SMB connection. That means terminating SMB3 encryption at the WAN accelerator on the left and generating new SMB encryption on the right. Basically, SMB3 proxies at both ends. That gets pretty complicated pretty quickly, but it also illustrates the importance of understanding where function boundaries belong. I'll also mention that SMB2 and SMB3 support Microsoft Branch Cache, which provides its own form of WAN acceleration. And of course, the WAN traffic may have to be encrypted as well. For tow cards, we already had the sockets API, or WinSock. For iSCSI, we had SCSI. The file system can do block I/O to SCSI or iSCSI or Fiber Channel without caring which is which. It's all just SCSI. There is no such boundary defined for SMB or for NFS that I know of. One goal of the Zambezi project is to create a draft specification of an SMB3 offload API. SmartNICs are called SmartNICs for a reason. They've got brains. The intelligence within the latest crop of SmartNICs is called a data processing unit, or DPU. These are multi-core RISC processors, most commonly ARM, but I know of 1 or 2 vendors using MIPS, and I'm hoping to see RISC-V at some point. DPUs are designed to support massive I/O throughput across multiple I/O channels. They are also built to be programmable and process messages quickly. They may even have general-purpose GPU cores included. Today, DPUs are typically found on high-end SmartNICs and developer boards, but they can also be added to computer mainboards. Their purpose is to offload I/O processing from the CPU. DPUs seem new to me, but they've been around for a couple of years in one form or another. They are established technology. Some manufacturers are already on their second-generation products. There are developer boards and tool chains available from multiple vendors, and most of these vendors have ambitious roadmaps for future products. We've talked about processing power on SmartNICs, and if you're familiar with the SNIA, you know that there's been a lot of activity around computational storage. That's processing power at the storage device. So we've got processing power on the edges. What about the middles? As you are probably aware, there are smart switches. These are network switches, and routers too, that have the ability to inspect packets and make decisions about how to handle those packets on the fly. The packets can be forwarded, discarded, or otherwise manipulated. Sonic is probably the best supported network operating system for smart switches. It's Linux-based. It was co-developed by Microsoft and the Open Compute project. It runs on multiple switches from multiple vendors across multiple ASICs, which are processors. It supports a switch abstraction interface, which is sort of like a hardware abstraction layer. It also supports the P4 programming language, which is a domain-specific language used to write packet forwarding programs. Distributed and shared file systems when the network really is the computer.
Binge dial.
We've got ubiquitous computing power here. There's RISC at the disk, switched on ASICs, and the DPU is meeting with the CPU. Across our network, we have computing power at every interconnect. With all of this computing power, where do we put stuff? The network is now a distributed computing environment, so we're going to have to pay attention to those function boundaries and modularize our code so that we can move our boundaries as needed. If we can offload SMB3, why not NFS? If we can offload shared file protocols like those, why not distributed file systems? And if we can do all of that, plus block storage, can we build complete storage systems within the network? What would the interface look like? Could we put the whole file system onto the SmartNIC? I'm mostly on my own with this project, though I have had some very useful copy editing submitted via a pull request. My experience with JSIFs was that it took a couple of years before the project got serious traction. For now, it's your friendly neighborhood open source project, and here's the link. Here are some references that I hope you will find interesting and/or useful. And please take a moment to rate the session.